Hello everyone! Today we're going to talk about hardware for artificial intelligence. In the previous lecture, I already touched on this topic, but today we'll dive deeper into it. Let's look at hardware like a whole team of superheroes who are completely different but often work together. Let me explain what I mean. Remember the movie Suicide Squad. I hope we have some fans of this movie here. For those who haven't seen it, it's a story about how government agent Amanda Waller assembles a team of supervillains to complete a secret mission. Each character has unique abilities. Harley Quinn, for example, is incredibly fast and flexible. Deadshot is a sniper with perfect accuracy. Killer Croc has raw physical strength. El Diablo can create firestorms of incredible power. And here's what's important. Hardware for artificial intelligence systems works exactly the same way. Different types of processors are like different superheroes. Each one is perfectly suited for their own tasks. Let's start with Central Processing Units, or CPU. This is our Harley Quinn in the hardware world. Why her exactly? Because CPUs are incredibly versatile and quickly switch between tasks, just like Harley switches between crazy ideas. Regular processors can perform complex operations that machine learning usually doesn't need. They're built for versatility, not for specialized artificial intelligence tasks. Central processors have just a few cores, usually from 2 to 16, but each core is very smart and can perform complex operations. Imagine that Harley can simultaneously juggle a bat, plan an escape, and tell a funny story. Many tasks, but each one requires full attention. Now meet our Killer Croc of the hardware world, Graphics Processing Units, or GPU. If CPU is precision and versatility, then GPU is pure computational power. Graphics processors were originally created for image processing, but it turned out they're perfect for machine learning. Why did this happen? They have thousands of cores. Each GPU core is quite simple, just like Killer Croc. He doesn't make complex plans, but when you need to break through a wall, there's no one better. Graphics processors are designed for massively parallel data processing. For small machine learning projects, GPUs usually outperform CPUs in performance, even if central processors have higher clock speeds. Now, let's talk about our team's sniper, specialized hardware for artificial intelligence. This is our Deadshot. If GPU is brute force, then specialized chips are precision and efficiency. There are special integrated circuits called application-specific integrated circuits, or ASIC, and there are also systems on a chip, system on a chip, or SoC. These solutions are created specifically for artificial intelligence tasks. They have cool features. First, multiple cores. Second, spatial data management. And third, the ability to perform calculations directly in memory. It's like if Deadshot can not only shoot accurately, but also reload his weapon without taking his eyes off the target. And now meet our El Diablo, Tensor Processing Units, or TPU. This is the most powerful weapon in the artificial intelligence arsenal. Google created TPU specifically for tensor computations. Cloud Tensor Processing Units are available in Google Cloud, and Edge TPU work directly on devices. It's like if El Diablo had a version for large-scale operations and a compact version for pinpoint tasks. And you know what makes TPU especially cool? They support low-precision arithmetic. Instead of 32 bits, they can use just 8. For machine learning, this is usually enough and much less energy is consumed. Let me make a small remark and explain what low-precision arithmetic and bits are in general. A bit is the smallest unit of information in a computer, which can be either 0 or 1. The number of bits determines how accurately a computer can represent a number. 32 bits accordingly allow representing about 4 billion different values, which gives very high precision for calculations. This is the standard for most regular computations. In turn, 8 bits give only 256 different values, which is much less, but for many machine learning tasks this is sufficient. This is called low-precision arithmetic, and this means we'll need less energy consumption and our calculations will be faster, less memory will be required, and there will be the possibility to place more computational blocks on the chip. I hope this is a bit clearer now. Now let's talk about where all these heroes work. There are two main approaches. cloud computing and edge computing. The cloud is like Amanda Waller's operations base. There are all the resources, powerful servers. You can train huge models. But there's one problem. You need a constant internet connection. Edge computing is when calculations happen directly on the device. It's like if each squad member could act autonomously in the field. For example, a smartphone with an artificial intelligence chip can recognize faces even without internet. Often a hybrid approach is used. The model is trained in the cloud where there's power and then deployed on the device where response speed is needed. Let's look at real manufacturers of artificial intelligence hardware. It's like meeting the creators of our superhero team. NVIDIA produces graphics processors and specialized AI processors, for example the Volta series. They're like the creators of Killer Croc. They specialize in brute computational power. Google developed TPU for training and inference. They have cloud versions and edge TPU for devices. This is the team that created our El Diablo. Intel offers Nirvana processors for deep learning and Movidius chips for computer vision. And there's also Mobileye, with IQ processors for cars. Imagine Deadshot, who specializes in road situations, and even Apple creates bionic chips for iPhone, and Huawei develops Kirin with built-in neural network processing. From a testing perspective, there will be several important aspects here. First, you need to consider that a model can work differently on different hardware. A model trained on powerful GPUs in the cloud might behave differently on a mobile chip. Second, performance can differ dramatically. What works in a second on TPU might take minutes on a regular processor. Third, new types of errors appear related to low precision arithmetic and parallel computations. It's like if our superhero team sometimes interfered with each other instead of working together smoothly. For the exam, it's enough to remember several key points. Machine learning usually benefits from hardware that supports low-precision arithmetic, can work with large data structures, and provides massively parallel processing. GPUs usually outperform CPUs for machine learning applications, even with higher clock speeds of central processors. And specialized hardware like ASIC and SoC is most suitable for edge computing, while model training usually happens in the cloud. Continuing our lecture. Did you know that modern GPUs can contain more than 5,000 cores? For comparison, top CPUs rarely have more than 64 cores. It's the same as having 5,000 of our superheroes instead of 5. So let's summarize. Hardware for artificial intelligence systems is like the Suicide Squad team. Each type of processor has its own superpowers. Central processors are versatile, like Harley Quinn. Graphics processors provide brute computational power, like Killer Croc. The specialized chips are precise and efficient, like Sniper Deadshot. And tensor processors have enormous power, like El Diablo. The choice of hardware depends on the task, budget, and performance requirements. It's important to understand these differences to effectively test AI systems on different platforms. And in the next lecture, we'll talk about artificial intelligence as a service, or AIaaS. It will be like studying whether you can rent superheroes instead of assembling your own team. I'll be waiting for you in the new lesson.